Now this session we are going to see the torsion of a cylinder in module 2, which is nothing but elastic properties of materials. What is the torsion of a cylinder? What is the torsion of a cylinder? A long body which is twisted around its length as an axis is said to be under torsion. That means a body which is twisted around its length as an axis. It is said to be under tension. The twisting is brought into effect by fixing one end of the body to the rigid support and applying a suitable couple at the other end. That means upper part of the long body is fixed and the lower part is allowed to twist. That gives rise to the torsion in a cylinder. That is what it means. The twisting is brought into effect by fixing one end of a body to a rigid support and applying a suitable couple at the other end. Consider a long cylindrical rod of radius R and length L, which is fixed at the upper end. As discussed, the cylinder, we are taking it as a rod which is fixed at the upper end, having a length of L, having the radius of the rod as R, and the lower end is free to move. Let OO dash be the axis of rotation. We will see in the next slide the diagram. Let us consider a rod of radius R and length L. Let OO dash be the axis of rotation. Imagine the cylinder is made up of thin, concentric, hollow cylindrical layers, each of thickness dr. If a cylinder is now twisted at the lower end and the moment is 0 at the fixed end and gradually increases at the lower end. That means we are taking a cylinder which is fixed at the upper end and we are rotating the other end of the rod, which is other end of the rod. Now you can see the diagram over here. The upper part, you can see in the diagram, upper part is fixed and the lower part of the rod is been allowed to make a twist, due to which here you can see the capital L is the length of the cylinder and capital R is the radius of the cylinder here. And as discussed in the before slide, it is made up of concentric layers of radius small r. Dr is the thickness of the concentric circles. That is what is mentioned over here. Small r is the radius from the center to the point of consideration, that plane of consideration or the concentric circle under which we are considered. Now let us see the diagram. Let us consider one concentric circular layer of radius r and thickness dr. Now if you look at the figure over here, look at the upper part here. Consider a small amount of dr, of thickness dr. Consider a concentric circular layer of thickness dr. You can see from the diagram easily, near the bottom part, dr is nothing but the one concentric circular layer having a radius of small r and the thickness of dr. Let x be on top remains fixed. Point B shifts to B dash. Let the point x, you can see on the upper part the point x is fixed and the lower part B is being shifted from B to B dash. Because upper part is fixed and we are giving a twist to a cylinder, lower part of the cylinder is being given a twist, due to which the B point B, which is at x from upper point x, be the fixed point at the upper part and B be the point which is being moved to B dash due to the twist given to the lower part of the cylinder. That is what it says. Now B x B dash is nothing but a phi. From the diagram you can see that B x B dash is nothing but a phi, which is nothing but an angle of shear. This is nothing but the, because of the twist, that is the angle that has been twisted by an amount from the upper part to the lower part. B dash is equal to L phi. As phi is small, I am taking as tan phi can be taken as phi. And B dash is taken as theta. From the figure you can take it as B O dash, B O and B dash. See here next to the diagram it has been given angle B x B dash is equal to phi. Angle B O B dash is nothing but theta. And B O dash is equal to B dash O dash is equal to R. Next to the diagram, right side of the diagram, we have given some angles bx b dash is nothing but phi, bo b dash is nothing but theta, bo dash is equal to o dash b dash, that is equal to r. So from this we are taking as L phi is equal to r theta from equations 1 and 2. L phi is equal from, see here from 1 and 2 we can make it as L phi is equal to r theta, or phi can be written as r theta by L. Area of a cylinder is nothing but 2 pi r into dr. So F is the shearing force. Then shearing stress T is equal to force per unit area. We know that force is nothing but the shearing stress. Therefore, shearing stress T is equal to force per unit area. F is the shearing force. And here stress is equal to force per unit area. Therefore, shearing stress T is equal to F by 2 pi r into dr. Now F is equal to, rearranging the terms, F is equal to T into 2 pi r dr. Let that be equation 4. Now since phi is the angle of shear and eta is the shearing stress by shearing strain, therefore T by phi, rearranging the terms, T is equal to N into phi. We know that phi is nothing but r theta by L. Therefore, substituting that here, we get T is equal to eta r theta by L. Substitute equation 5 in equation 4. What is equation 4? Here we have got it as F is equal to T into 2 pi r into dr. Substitute the value of T into this equation. Here we are getting here as F is equal to eta r theta by L into 2 pi r dr, which is we have taken from the equation 4, the value of equation 4 in equation 5. So what we are getting here, F is equal to eta r theta by L into 2 pi r dr. Rearranging the terms, 2 pi eta theta by L is into r square dr. Just rearranging the terms in the equation 6, you are getting the moment of force about O dash is equal to 2 pi eta theta by L into r square dr into r. It is nothing but force into perpendicular distance. Moment of force we have discussed, force into perpendicular distance. From equation 6 we have got the force, perpendicular distance is r. So rearranging the terms, you get it as 2 pi eta theta by L into r cube dr. Now this is regarding only to one cylinder. If we consider that entire cylinder where small r is equal to 0 capital R, as capital R is the radius of the rod which we have considered. So it is integrated from small r equal to 0 to small r is equal to capital R, because we have considered one concentric circular cylinder having a radius of small r. So we want to have it for the whole cylindrical rod. Therefore, we are integrating for the entire rod from 0 to capital R and integrating. It is 2 pi eta theta by L into r cube dr. Therefore, twisting couple acting on the entire cylinder is the same equation I have written again to have continuity. That is equal to 2 pi eta theta by L into r to the power of 4 by 4 under the limits 0 to r are the upper and lower limits. Since integration is from 0 to r, lower and upper limits becomes 0 is the lower limit and capital R is the upper limit. And integral of r cube is nothing but r to the power of 4 by 4. So applying the limits and rearranging the terms, you are getting pi eta r to the power of 4 into theta by 2L. This is the couple per unit twist is given by C is equal to couple acting on a wire divided by angle of twisting. Therefore, pi eta r power 4 theta by 2L into divided by theta, because C is nothing but the couple acting on wire per angle of twisting. Angle of twisting is nothing but theta. Therefore, substituting value of C is pi eta r power 4 theta by 2L divided by theta. Rearranging the terms, theta gets cancelled. So, couple per unit twist is given by pi eta r power 4 by 2L. So, this is the couple per unit twist of a solid circular cylinder. which is nothing but the torsion of a cylinder. Thank you.